A black hole with the mass of 100 billion suns. Its event horizon is bigger than our entire solar system, 130 times Neptune's orbit. If you fell toward it, you'd travel farther than from the Sun to Pluto before reaching the point of no return. This monster exists right now, devouring everything around it. Today, we're hunting Phoenix A, the biggest black hole ever discovered. Let's dive in.
Let's get straight to the point. You want to know about the most massive black holes in the universe? Here's your top 3. Number 3, the black hole at the center of IC 1101. This supergiant elliptical galaxy harbors a monster weighing in at about 40 billion times the mass of our Sun. To put that in perspective, the black hole at the center of our Milky Way, Sagittarius A star, is only about 4 million solar masses. This thing is 10,000 times more massive than our galactic center. Number 2, TON 618, the legendary beast that's been terrifying space enthusiasts for years. This quasar's central black hole tips the scales at roughly 66 billion solar masses. Its event horizon, the point of no return, is about 1,300 times larger than the distance from Earth to the Sun. If you place it at the center of our solar system, the event horizon would extend well beyond Neptune's orbit. And now, the heavyweight champion, Phoenix A. Sitting at the heart of the Phoenix cluster, this absolute monster weighs approximately 100 billion solar masses. 100 billion! That's not just big, that's incomprehensible. To give you some context, if our Sun were a golf ball, Phoenix A would be larger than the entire observable universe in comparison. Okay, that's an exaggeration, but you get the point. We're dealing with something so massive that our brains literally can't process the scale. So where is this cosmic nightmare hiding? And just how big are we really talking? Let's zoom in.
Phoenix A lives at the center of the Phoenix cluster, a massive collection of galaxies located about 5.8 billion light-years away from us. That means the light we see from it today left that region when Earth was still in its early days, long before complex life existed. Now I know what you're thinking. 100 billion solar masses sounds insane. But what does that actually mean in real terms? Let me break it down for you. First, let's talk about the event horizon, the boundary around a black hole beyond which nothing, not even light, can escape. For Phoenix A, that event horizon has a radius of approximately 590 billion kilometers. To put that in perspective, the distance from the Sun to Neptune is about 4.5 billion kilometers. Phoenix A's event horizon is more than 130 times larger than Neptune's entire orbit. If you could somehow line up suns side by side from the center of Phoenix A to its event horizon, you'd need about 4 million of them. 4 million suns just to span a radius. But here's what really gets me. Despite being unimaginably massive, Phoenix A isn't even that large physically compared to some stars. Remember Stephenson 218 from our previous video? That star's physical radius is actually larger than Phoenix A's event horizon would be if Phoenix A were the same mass. But the difference is density. Phoenix A has packed 100 billion solar masses into a region of space that, while huge by human standards, is absolutely tiny on cosmic scales. And here's the kicker. All of that mass is compressed into a singularity at the center, a point of infinite density where the laws of physics as we know them completely break down. Everything that falls into Phoenix A, stars, planets, gas clouds, light itself, gets crushed down into that single point forever. This isn't just a black hole. This is a cosmic predator that has been devouring everything around it for billions of years. But what would happen if this monster suddenly appeared in our neighborhood? Let's run a terrifying thought experiment.
Okay, Imagine this. We take Phoenix A and swap it with Sagittarius A's star, the supermassive black hole at the center of our Milky Way galaxy. What happens to us? To Earth? To our entire galaxy? First, let's remember that Sagittarius A's star has a mass of about 4 million solar masses. Phoenix A, 100 billion solar masses. That's 25,000 times more massive. This isn't an upgrade. This is a catastrophic replacement. The immediate effect? Gravitational chaos. Phoenix A's immense gravity would completely reshape our galaxy. Stars that were in stable orbits around Sagittarius A star would suddenly find themselves in drastically different trajectories. Some would be flung out of the galaxy entirely, ejected into the void of intergalactic space at incredible speeds. Others would spiral inward, doomed to be consumed by the monster at the center. But what about us, Earth? Since about 26,000 light-years from the galactic center, would we be safe at that distance? Honestly, probably not in the long term. While we wouldn't immediately fall into Phoenix A, the gravitational disruption would destabilize the orbits of countless stars throughout the galaxy. Star systems that were once safely distant from each other would suddenly be on collision courses. Close encounters between stars would become far more common, and any one of those encounters could fling Earth out of our solar system or send us careening into the sun. And here's the really terrifying part. Phoenix A would likely be actively feeding. A black hole this massive doesn't just sit there quietly. It pulls in vast amounts of material, gas, dust, entire stars, forming what's called an accretion disk. This disk heats up to millions of degrees, emitting intense radiation across the entire electromagnetic spectrum. X-rays, gamma rays, ultraviolet light, all of it flooding the galaxy. If Earth were anywhere near the galactic center, that radiation alone would sterilize the surface. We're talking about energy levels so intense that they would strip away our atmosphere, boil our oceans, and make the planet completely uninhabitable. Even at our current distance, the increased radiation levels could severely damage the protective ozone layer, exposing all life to harmful cosmic rays. The night sky would look completely different too. Instead of the faint glow of the galactic center we see now, there would be a blazing beacon of light. A quasar shining brighter than billions of stars combined. Ancient civilizations would have built their entire mythologies around this terrifying cosmic lighthouse. Phoenix A wouldn't just change our galaxy, it would fundamentally break it. But how does a black hole even get this massive in the first place? What kind of cosmic process creates a monster like this?
Here's the thing about supermassive black holes. We still don't fully understand how they form, but we have some pretty solid theories. Black holes don't start out as giants. Most black holes form when massive stars with at least 20 times the mass of our Sun, reach the end of their lives and collapse in a supernova explosion. The core compresses into a black hole weighing maybe 10 to 100 solar masses. That's how you get stellar mass black holes. But Phoenix A isn't 100 solar masses, it's 100 billion solar masses. So what happened? The answer is a combination of growth mechanisms that have been working for billions of years. Think of it like this. Phoenix A started small, probably as a seed black hole in the very early universe, and then it grew, and grew, and grew. One way black holes grow is by feeding. Every time a black hole consumes matter, whether it's gas, dust, or entire stars, it adds that mass to itself. In the dense environments of early galaxies, black holes had access to enormous amounts of material. They gorged themselves on clouds of primordial gas, swallowing millions of solar masses worth of fuel. But eating alone can't explain Phoenix A's size. There's another mechanism: mergers. When two galaxies collide, their central black holes eventually spiral toward each other and merge into a single, larger black hole.
This process releases tremendous amounts of energy in the form of gravitational waves, ripples in space-time itself. Phoenix A likely formed through countless mergers over billions of years. Every time its host galaxy consumed another galaxy, Phoenix A would merge with that galaxy's central black hole, adding its mass to the total. It's like a cosmic snowball effect. The bigger you get, the more you attract, and the faster you grow. But here's where it gets really interesting. There's a limit to how fast black holes can grow through feeding. It's called the Eddington limit. Basically, when a black hole feeds, the infalling material heats up and releases radiation. If the black hole tries to eat too fast, that radiation creates an outward pressure that pushes material away, limiting how quickly it can grow. Phoenix A somehow managed to exceed or bypass this limit repeatedly over billions of years. Maybe it went through periods of super Eddington accretion, where it fed faster than theoretically possible. Maybe it had access to unusually cold gas flows that didn't produce as much radiation. Or maybe it's just been around for so long that even slow, steady growth eventually built it into the monster we see today. Whatever the process, the result is clear. Phoenix A is the culmination of billions of years of cosmic violence, consumption, and growth. And it's not done yet. This monster is still feeding, still growing, still pulling in everything around it. Which brings us to the final question. What's it actually like near this thing? Let's talk about what actually happens near a supermassive black hole like Phoenix A. Because this isn't just an empty void sitting in space. This is one of the most violent, energetic environments in the entire universe. First, there's the accretion disk. As material falls toward Phoenix A, it doesn't just plunge straight in. Instead, it spirals inward, forming a massive rotating disk of superheated gas and plasma. We're talking about temperatures in the millions of degrees, hot enough to emit X-rays and gamma rays that can be detected from billions of light years away. The disk around Phoenix A is absolutely enormous. We're talking about a structure that could easily span several light years across. For comparison, the nearest star to our Sun is about 4 light years away. The accretion disk around Phoenix A could potentially engulf multiple star systems at once. And the energy output? Absolutely insane. When matter falls into a black hole, it converts mass into energy far more efficiently than nuclear fusion in stars. In fact, a black hole converting matter to energy is the most efficient energy production mechanism we know of in the universe. Phoenix A, actively feeding on its surroundings, can outshine entire galaxies, billions of stars worth of light coming from a region smaller than our solar system. But here's where it gets even crazier. Black holes don't just pull things in, they can also push things out. Through a process we don't fully understand, supermassive black holes can launch enormous jets of plasma traveling at nearly the speed of light. These jets shoot out perpendicular to the accretion disk, extending for hundreds of thousands of light years into space. Phoenix A's jets, powered by its immense mass and spin, could easily stretch across multiple galaxies. Anything in the path of these jets would be bombarded with intense radiation and high-energy particles. If a star system happened to be in the line of fire, it would be sterilized completely, all life vaporized in an instant. Now, imagine you're somehow approaching Phoenix A in a spacecraft. What would you experience? First, you'd notice the light. The accretion disk would be blindingly bright, a swirling infernal of colors you've never seen. Ultraviolet, X-rays, wavelengths your eyes can't even detect without instruments. The heat would be intense even from a distance, overwhelming any shielding your ship might have. As you got closer, you'd start to feel the effects of tidal forces. See, gravity isn't uniform across your body when you're near a black hole. Your feet, being slightly closer to the black hole than your head, would experience stronger gravity. Near Phoenix A's event horizon, this difference becomes extreme.
You'd be stretched like taffy in a process scientists cheerfully call spaghettification. And then, the event horizon. That invisible boundary 590 billion kilometers from the center. The point where escape velocity exceeds the speed of light. Cross that line, and your fate is sealed. No amount of thrust, no amount of energy could ever get you back out. You'd fall inward, watching the universe behind you redshift and fade as you're pulled inexorably toward the singularity. Time itself would behave strangely. To an outside observer, you'd appear to slow down as you approach the event horizon, never quite crossing it. But from your perspective, you'd cross it in finite time. And then? Well, we don't really know what happens at the singularity. Physics breaks down. Our equations give us infinities. It's the edge of our understanding. Phoenix A represents the ultimate cosmic mystery and the ultimate cosmic terror. A region of space where 100 billion suns worth of mass has been compressed into a point of infinite density, warping space-time itself beyond recognition.
Phoenix A isn't just the biggest black hole we've found. It's a reminder of how extreme the universe can get, how violent, how massive, how incomprehensible the cosmos really is. And somewhere out there, there might be even bigger ones waiting to be discovered. The universe has a way of surprising us like that. Thanks for watching. If this blew your mind, smash that like button and subscribe for more cosmic content. Should we explore neutron stars next? Or maybe the mystery of dark matter? Let me know in the comments. Until next time, keep looking up.